Good morning, welcome to new lecture. Today I will talk about equilibrium of a particle. So, today's topic is equilibrium of a particle. What is the particle? I defined before particle, any object, the size is small and we can neglect the size and we assume only it has a mass and we will not consider the size, we will call it particle. In order to have one particle in equilibrium, for example, assume we have one particle, this particle is subjected to different forces, for example F1, F2, F3, F4, F5, and so on. So, in order to have this particle in equilibrium, the summation of forces or resultant force act on this particle should be equal to the zero. So, let's say define, we call it a particle is at equilibrium if it remains at rest or has a constant velocity. This is the definition of equilibrium. If a particle is at equilibrium if it remains at rest or has a constant velocity, we will call it that particle, it is in equilibrium. So in order to have particle in equilibrium, summation of all forces should be equal to the zero, or resultant force should be equal to the zero. If we have a particle in two dimensions, let's assume our particle, it is in two dimensions. In two dimensions we have two directions, one horizontal direction, another vertical direction. So y, x, 2D dimension. If we have a particle in two dimensions, in order to have this particle in equilibrium, as I mentioned, the summation of forces should be equal to zero. So there are, for example, 4 forces or 100 forces act on this particle in two dimensions. We want to satisfy equilibrium condition. We want to see this particle, it is in equilibrium or not. So the summation of all forces means resultant force should be equal to zero. In order to simplify this relation, we can decompose all forces one by one in x and y direction, because in two dimension space or in two dimension plane, we call it in plane structure or particle, we have two dimensions, one it is x direction, another y direction. We can decompose all forces one by one in the x direction and y direction. So summation of all forces equal to zero, it means summation of all forces in x direction should be equal to zero, and summation of all forces in y direction should be equal to zero. So in two dimensions we will decompose all forces one by one in the x and y direction. Then we will add all forces in the x direction together, and summation of all forces should be equal to zero. In that case, particle will not move in the x direction. Summation of all forces in the y direction is equal to zero. In that case, particle will not move in the y direction. In 3D space, because we have 3 dimensions, so summation of forces equal to 0. It means summation of forces in the x direction equal to the 0, summation of forces in the y direction is equal to 0, and summation of forces in the z direction is equal to 0. So again, if we have particle and several forces act on this particle, summation of forces or resultant force is equal to 0. This means summation of forces, if we decompose force in the x, y, z direction, summation of all forces in the x direction is equal to 0, summation of all forces in the y direction equal to 0, and summation of all forces in the z direction is equal to 0. So, in order to test, to see a particle in 2D space is equal to the, in 2D space it is at equilibrium, or in 3D space it is at equilibrium, we should check to see if summation of forces is equal to 0. In 2 dimension, in 2D space, we have only 2 directions, so we can decompose forces in the x and y direction, and if summation of forces in the x direction is equal to 0 and summation of forces in the y direction is equal to 0, we can say this particle in 2D space it is at equilibrium. In 3D space, again we can decompose all forces in the x, y, z direction, and if summation of forces in the x direction is equal to 0 and summation of all forces in the y direction is equal to 0 and summation of all forces in the z direction it is equal to 0, we will call this particle it is at equilibrium in 3D space. So I will solve different examples and you will see how we can investigate, how we can look at to see this particle it is at equilibrium or not. But the condition for testing to see this whether this particle it is at equilibrium or not in 2 dimensions, summation of forces in the x direction equal to 0, summation of forces in y direction is equal to 0. We should first decompose force in the x and y direction and check these conditions. In 3D space, summation of force in the x equal to 0, summation of force in y direction should be equal to 0, and summation of forces in the z direction should be equal to 0. Let's define new term, because we will need in this course and later on, in order to solve a lot of different real life problems, we should know that term and we should able to draw the free body diagram. So I should first define the free body diagram. What does that mean, the free body diagram? Free body diagrams are diagrams used to show the relative magnitude and direction of all forces acting upon an object in given situation. For example, assume we have hanging weight. This is ceiling and there is a hanging weight here. The mass for this weight, it is M. So the good example, it is hanging weight. So let's look at to see what is the free body diagram here. For example, this mass, it is one small box or something like that. Here our particle, it is box because we want to look at to the equilibrium of that box. So in order to draw free body diagram, first we will release this object or particle from surrounding. So we will release that, we will cut that, and we will look at to the box. Now, what are effective forces acting on this box? One of them, it is the tensile force in this cable. Another force, it is gravity force, or it is weight, which is equal to mass times gravity acceleration. So this will be a free body diagram for this box. Or let's look at another example. Assume there is a box on this desk and again the mass of this box, it is M. Let's look at the free body diagram for this box. The free body diagram for this box will be the box and effective forces on this box. One of them is reaction of the desk and another, it is the weight of the box, mg. So this will be the free body diagram for this box. Or again, if we have one box on ground surface and using one rope, I am pulling this box with the force of F. Now free body diagram for this box will be this force I am applying, the normal reaction of the ground to the box, the weight of the box to the ground, and the friction force which resists against the movement of this box. Now all forces acting on this box, it is 1, 2, 3, 4 forces. This is the meaning of the free body diagram. Let's look at one simple example. Assume we have one pulley, and in this course we assume the pulleys, they have negligible weight. We will not consider the weight of the pulleys and cable. We have cable and there is one box here hanging, and I apply tension force T here. What is the free body diagram for this system? We can draw different free body diagram here. One of them for pulley, the free body diagram for pulley, this is T I am applying. This T will transfer through this rope and it will transfer to this box. So if I cut like this system, the free body diagram for pulley, this will be T, this will be T, and there is another force here in this cable, I show with F. This is free body diagram 1. Another free body diagram I can draw for the box. This is the box. This is the cable force because I cut here. This is T, this is T, and weight of the box. So this will be free body diagram number 2. Free body diagram, we should know how to draw it because it will make easier our calculation. Using free body diagram, we can simplify very complex system to the simple system, and we can see we can look at to see what is going on, and it will be easy to understand the concept. Let's look at to one problem to see how we can solve this problem using free body diagram. There are 3 cables and 1 box here. The mass for this box, it is 2 kilogram, 4 meter, 3 meter. This is 3 meter. So if I assume this angle is beta, this angle is alpha. If this is 4, this is 3, the length for this cable, it will be 5 meter. Now, I want to find, let's A, B, C, D. I want to find the tension force in each cable to see how much force we have in each cable. Let's look at the free body diagram. First free body diagram, I will look at the equilibrium of this box. So I will cut like that, and I will release the box from surrounding. So this will be TAD. I want to find that, it is unknown. Another force, it is weight for this box, it is 2 times gravity 9.81. From here we see this box, it is in 2D space, so summation of forces in the x direction, it will not help us, but summation of forces in y direction equal to 0. From here I can write TAD minus 2 times 9.81 is equal to 0, and from here I can find tension force in the rope AD. It will be 2 times 9.81. This was our first free body diagram, so free body diagram 1. Let's look at the next free body diagram. Next free body diagram, I will cut from here. So, next free body diagram, I will look at the equilibrium of point A, T, AC, T, AB, this is TAD, which I found it was 2 times 9.81. This is beta angle, this is alpha angle. Beta angle, it is 45 degrees, it is clear, because from here to here it is 3, from here to here it is 3. So beta angle, it is 45 degrees. Now, if I write summation of forces in the x direction is equal to 0 because this point A should be at equilibrium. In order to have point A in equilibrium, it should not move in horizontal direction. That means summation of forces in the x direction should be equal to 0. So I can write here in this free body diagram number 2 here TAB, if I want to decompose in the x direction, it will be TAB sine alpha. Sine of this angle will be 4/5. So TAB times sine alpha 4/5 minus TAC sine of beta. Sine of beta, beta is 45 degrees, it will be square root of 2/2 is equal to 0. Another equilibrium equation is summation of forces in y direction is equal to 0. Summation of forces in y direction is equal to 0. I can write, I will decompose all force in y direction. And in the x direction, TAB, there is no projection of AB in the x direction. If I project TAB in the x direction, because it is perpendicular to that direction, it will be 0. So you don't see that AD in the equilibrium equation, because AD is perpendicular to the x direction. Summation of force in the y direction, it will be TAB, tension in the AB, cosine alpha, that will be 3/5 plus TAC cosine beta, cosine of 45 square root of 2/2 minus TAD, which is 2 times 9.81 is equal to 0. Here you see we have two equations and two unknowns, AB and AC, AB and AC. Two equations, two unknowns, so we can find both forces. From here, TAC, if you solve it, you will find TAC 15.86 Newton and TAB will be equal to 14 Newton. Let's a little bit briefly talk about Hooke's law as well. Of course you know that, but if we have one linear spring and we apply force, what is the relation between force and displacement in that spring? That we can represent using Hooke's law. So if we have one spring, if we have one linear spring and I apply force F, here is a spring, I apply force F. If I apply force F in this spring, I will have elongation like X. What is the relation between F and X? That we call it Hooke's law. First, Hooke, he defined the relation between F and X. For that reason, we call it Hooke's law. He is a British scientist, and he was in the Newton's time. So this law is very famous. Hooke's law states that the force needed to extend or compress a spring by some distance x Hooke's law states that the force needed to extend or compress a spring by some distance x scales linearly with respect to that distance. So Hooke's law states that the force needed to extend or compress a spring by some distance x scales linearly with respect to that distance. What does that mean? If we have one spring and we apply force F, definitely we will have elongation in that spring. I show with X. Let's do one simple experiment. First, we don't apply any force to this spring, so the elongation or displacement, it is 0. I will show that in the one diagram F respect to the X. So I will draw one line in the horizontal direction. This axis, it is x-axis, it is elongation in the spring, and the vertical axis, it represents force inside of the spring. So if I don't apply any force, displacement is 0. It means 0, 0, this point. If I increase force from 0 to one certain magnitude, such as F1, in that case, the displacement will be x1. So this is x1, this is F1. If I increase the force to the F2, displacement will be x2, and so on. If I attach these points, I will end up with one inclined or diagonal line. This line gives us the relation between force and displacement in one linear spring. So the slope of this line, if this angle is alpha, the slope of this line means tangent alpha is equal to force divided by displacement, because if we look at to this shape, this is triangle, tangent of this angle is equal to force F divided by X. In this triangle, tangent for this angle is equal to force divided by X. This tangent alpha we will show usually with K, and they call it stiffness of a spring. So this K, it means tangent of alpha in this diagram, and we call that stiffness of a spring. So tangent alpha is equal to K, that equal to F divided by X. This K, it is stiffness of a spring. From here, the formula for linear spring, relation between F and X, it will be equal to F is equal to K times X. This is spring formula, and first Hooke's, he developed this relation, and you see the force and displacement, they are proportional. Force and displacement, it is proportional. So F is equal to Kx. F here is effective force acts on spring. X is the elongation or displacement or deformation of spring. K is stiffness of spring. And how we will find K? We can draw this graph, and the tangent alpha will give us the K for one spring. So this is the concept of Hooke's block. Let's look at now to this problem. We have 3 springs, 1 spring, 2 springs, and 3 springs. Here we have box, the mass is 2 kilogram, point A, point B, point C, point D. The stiffness for this spring AD is 40 Newton per meter. The stiffness for this spring K AB is equal to 30 Newton per meter. The stiffness for this spring KAC is equal to 20 Newton per meter. Dimension here is 3 meter again, this is 4 meter, and this is 3 meter. Problem statement says determine the stretch in each spring for equilibrium of 2 kilogram block. So we have block here, the mass for that block it is 2 kilogram, and we are hanging this block using 3 springs, spring AD, AC, AB. You see the length, the distance 3 meter, 4 meter, 3 meter, and the stiffness for this spring, the stiffness for these springs are given. The stiffness for spring AD is 40 Newton per meter. The stiffness for spring AB is 30 Newton per meter. The stiffness for spring AC is 20 Newton per meter. We want to find elongation in each spring. In order to find that, first we should find the internal force in each spring. Internal force in each spring I found it in previous example. Instead of spring I put rope. It is the similar problem, and the internal forces will be identical. Why? Because again we can solve in similar way. So this is free body diagram 1. For this block it is the weight 2 times 9.81. The spring force here, F for example AD. This is free body diagram 1. So what is the force AD? Force AD we can write summation of forces in vertical direction is equal to 0. From here F AD minus 2 times 9.81 is equal to 0. So FAD will be equal to 2 times 9.81. So now I know what is the internal force in this spring. So what is the deformation for this spring? Force AD is equal to stiffness of spring AD times the deformation of this spring. So from here the force it is 2 times 9.81. The stiffness for that spring it is 40, it is given. So X AD or deformation or elongation for that spring will be equal to 0.49 meter. Now I will move to the point A and I will look at the equilibrium of point A, so I can find the internal force in the spring AC and AB. After finding force inside of AC, force for member AC divided by stiffness of AC will give us the elongation for AC. Force in AB divided by stiffness of AB will give us the elongation for AB. Let's do it. So point A, again, this is spring force AC, this is spring force AB, this angle beta, this angle alpha, and this is force AE. If you remember, beta was 45 degrees. We can calculate that. Summation of forces in the x direction is equal to 0. From there we can write F A B sine of alpha. Sine of alpha will be 4/5 minus F A C sine of beta, square root of 2/2 is equal to 0. Summation of forces in vertical direction is equal to 0. From there we can write F A C sine cosine of beta, square root of 2/2 plus F A B cosine of alpha, that will be 3/5 minus FAD. FAD is equal to 2 times 9.81. So minus 2 times 9.81 is equal to 0. From here we can find FAC is equal to 15.86 Newton and FAB is equal to 14 Newton. After finding the forces, the internal forces in these springs, I can write FAC is equal to KAC times XAC. From here, I can write XAC is equal to 15.86 divided by 20, that will be 0.79, and FAB will be equal to KAB times XAB, that will be equal to XAB is equal to 14 divided by 30, the stiffness, that will be 0.46 meter. So I found internal force in each spring, then I found elongation in each spring. Let's look at to the next example. Next example, we have two springs and the length for each spring it is 3 meters. So we have one spring and we have another spring. We attach this spring to the wall. The length for each spring it is 3 meters. So we have spring 1, spring 2, for example point A, B, C. We have two springs and the length for each spring it is 3 meters and the stiffness of each spring it is equal to 500 Newton per meter. So KAB is equal to KAC, that is equal to 500 Newton per meter. Then I apply force here at point A. So you see we attach the point B to the wall, point C to the wall, and point A is one ring. We attach each spring end to that ring. I apply force here and I pull this spring in this direction from right to left. In that case, we will have elongation in each spring, and point A will move to point A prime, and the shape for our system will be something like this because I apply force F. Problem statement says AA prime, so this deflection is 1.5 meter. So initially it is here, and the length for each spring it is 3 meters. Then I apply force here and I pull it, so it will deflect, and the deflection magnitude it is 1.5 meter. How much force I should apply? What is the force here? What is the force here? In order to find the force, I can look at the equilibrium point. So this is point A prime. Spring AB, spring AC. So F AB, F AC, and here I apply force F. Because this system is symmetrical, this is alpha, and I can find the alpha. So if I write summation of forces in the x direction is equal to 0, what I have, I can write FAB cosine alpha. Cosine alpha here, if this is 3, this is 1.5. From here to here it will be the square root of 11.25. So it will be FAB times cosine alpha, it will be 1.5 divided by square root of 11.25 plus FAC cosine alpha again times 1.5 divided by square root of 11.25 minus F is equal to 0. On the other hand, if we write summation of forces in the y direction equal to 0, I can write FAB sine alpha. Sine alpha will be 3 divided by square root of 11.25 minus FAC sine alpha again 3 divided by square root of 11.25 is equal to 0. From this relation, if I take the other side, this 3 over the square root of 11.25 and 3 divided by square root of 11.25, they will cancel from both sides, and from here we can understand FAB should be equal to FAC. So the internal force in each spring, they should be equal. So here, because FAB is equal to FAC, I can plug here instead of ACAB. In that case, I can write this 2 times FAB times 1.5 divided by square root of 11.25 minus F is equal to 0. Now, what is the FAB in the spring? FAB in the spring, will be stiffness of that spring times deformation of that spring. The stiffness of that spring is given, it is 500 Newton per meter. But what is the elongation or deformation in that spring? The length now it is A prime B. The length now it is A prime B, and you see this is one triangle 3 1.5, so we can find this length. This is 3 meter, this is 1.5 meter, so the square root of 3 squared plus 1.5 squared will be square root of 11.25. We can find that. So the length now, after applying the force, it is the square root of 11.25. Or I can write the square root of 3 squared plus 1.5 squared. The initial length was 3 meters. So the current length, A prime B, minus initial length will give us the deformation in the spring, or XAB. XAB times KAB will be force AB. So force AB from here will be 177.05 Newton. If I plug this force here, I will find the force I need to apply in order to move point A to point A prime. That will be, if you put here 177.05 Newton, you will find that force 158 Newton. Now, let's look at the problems. Last session I assigned you and I asked you to solve yourself, but now I will review those problems. First problem, there was a support and this support is subjected to 6 Newton, 8 Newton, 6 kilonewton, 8 kilonewton, and another force F. Magnitude is unknown, but direction is 30 degrees. Problem statement said find the F so that the resultant force for these three forces is as small as possible. So let's see if I find the resultant for 6 and 8. What is the resultant force? From triangle rule, this is 6 kilonewton. This will be 8 kilonewton. The resultant force for these two forces I can find using this triangle. So that will be, if I show it F prime and this angle is theta, F prime will be equal to square root of 6 squared plus 8 squared. That will be 10 kilonewton. And the theta will be equal to inverse tangent of 8 over 6. That will be 53.13 degrees. So now I found the resultant force for 6 and 8, and it is 10 kilonewton the magnitude, and the direction with horizontal direction it will be 53.13 degrees. Now I will find the resultant force for this F prime and F. Again I can find using triangle rule or parallelogram law. Now what I have, horizontal direction, I have this force F prime, which is 10 kilonewton, and this angle it is 53.13 degrees. F angle with horizontal direction, if this is 30, if I continue like this, this will be 30 degrees as well. This will be 30 degrees. So if I follow parallelogram law, I draw parallel to that. So this will be F prime, which is 10 kilonewton, and this will be F. I don't know the magnitude of the F, But if this is 30 degree and these two lines they are parallel, so this will be 30 degree and this is 53.13, so this angle will be 53.13. So entire this angle will be 30 plus 53.13, that will be equal to 83.13 degree. So entire that angle in that parallelogram will be 83.13 degree. Resultant force will attach this point to the tip of F. In order to have resultant force minimum, we should choose the length for F so that the F and this resultant force, they should be perpendicular to each other. Because if it is longer than that, this will not be 90 degree, and look at here, the magnitude of Fr, the resultant force will be longer. Or if it is shorter than that, again for example here, the length for Fr will be longer than this. So in order to make the total resultant force minimum length or minimum magnitude, the direction of this F and this Fr, they should be perpendicular to each other. If they are perpendicular to each other, in this triangle I can write law of sines. I can write F divided, this F divided by, if this is alpha, sine alpha is equal to Fr divided by sine 83.13, that is equal to 10 divided by sine 90. Look at this triangle. F divided by sine alpha is equal to Fr divided by sine 83.13, that is equal to 10, this length is 10, divided by sine 90. Sine 90 is 1, so this will be 10 over sine 90, it will be 10. Sine alpha, you can find sine alpha, because alpha here, you can find that, because if you add all these together, it will be 180 degree. So from here you can find alpha, or the summation of all angles in one triangle should be 180 degrees. So alpha plus 83.13 degree plus 90 degree should be equal 180 degree. Summation of all angles in one triangle should be 180 degree. Alpha plus 83.13 plus 90 degree is equal to 180. So from here you can find alpha. If you find alpha, you plug here, you can find F and Fr. I'm writing the final result. Fr will be 9.93 kilonewton and F will be 1.2 kilonewton. Let's look at the next example. Next example, there was one cassette plate and that was subjected to 4 forces, and we want to find the resultant force. So this is cassette plate, 4 forces, F1 magnitude 8 kilonewton, 4, 3, F2 4, 3 magnitude magnitude is 6 kilonewton, F3 4 kilonewton, F4 6 kilonewton. So we want to find resultant force for this force system. The easiest way, you can follow triangle rule, parallelogram law, but here you can decompose in the x and y direction and find the summation of all force in the x direction, summation of force in the y direction, and then you can find resultant force. So let's look at the summation of all forces in x direction, or summation of resultant force in x direction. That will be F1 in the x direction. If I decompose F in the x direction, will be 8 times 4 over 5. This is F1 is 8. If this angle is alpha, F1 cosine alpha, that will be 8 times 4 over 5 plus F2, that will be 6 times, again, cosine of this angle, it will be 3 divided by 5 minus 4 F3, because in inverse direction, minus 6 is equal to, if you calculate this, you will end up with 0. So the summation of all forces in the x direction will be equal to 0. F1 cosine of F1, it means 8 times 4 over 5 plus 6 times 3 over 5 minus 4 minus 6 is equal to 0. If you add, you will find equal to 0. Summation of all forces in y direction, that will be equal to, this will be in inverse direction of y, so it will be negative 8 times sine of that angle will be 3 over 5 plus 6 times 4 over 5 and there is no any, if we decompose F3 and F4, there is no component in the y direction, those they will be 0, and from here this will be again 0, because 6 times 4 24, 8 times 3 24, negative positive 0, and here again if we add we will get 0. And you can add it, you will see I'm right. So I found the resultant force in the x direction, resultant force in the y direction. So total resultant force will be the square root of Frx squared plus Fry squared, and because both of them is 0, it will be equal to 0. Okay. Let's say assign problem for you. You will think about that and try to solve it for next session. They are very simple problems. First problem, we have this system, support here, one cable, another cable, another cable, support here, and there is one block here. The weight for this block, it is 30 kilogram. Point A, B, C, D, E. So, for example, so we have this system, and orientation for this cable 3, 4, 5, and this angle, it is 60 degrees. We want to find internal force in each rope or cable, so we want to know what is F, B, D, what is the F, B, C, what is F, A, B, what is force A, E, what is force A, H. So, we have these cables or ropes. We are hanging 130 kilogram block here, and you see the orientation, and these are support as well we attach to the wall. What are the internal forces in each cable and ropes? Next one, this system was in 2D plane, U side. Let's look at today one example in 3D space. We have 3D coordinate, X, Y, Z direction. We have point A here, and this is point O. Point A here in the X direction, the coordinate, it is 1.5 meter, and in the Y direction, coordinate, it is 2 meter. We attach one rope from point A to point B. Point B is here, and the coordinate for point B in the Z direction, again, it is 1.5 meter. So this will be our rope. So we have AB rope. I call it, this is AB, yeah. We have another rope here in this direction. I call it AC. I have another rope here in this direction, AD. So I have 3 ropes. One of them parallel to the Y direction, another parallel to the X direction, another one it attaches point A to point B, and you see the point A coordinate, point B coordinate. We are hanging one flower pot here. The flower pot mass, it is 40 kilograms. So the flower pot mass, it is 40 kilograms. We want to find internal forces in each cable. We want to find internal force in rope or cable AB, AC, AD. Another example. We have pulleys and cables, and we have 2 cables and 1 pulley. The cords A, B, C, this is one cord or rope, and the cord BD comes from the support on the wall to the center of the pulley. Each support a maximum load of 100 pounds. So we have 2 rope. One of them A, B, C, another B, D. Each can support maximum load of 100 pounds. So if the load developed in each rope is greater than 100 pounds, will not sustain, can maximum sustain for 100 pounds. Determine the maximum weight of the box and angle theta for equilibrium. Determine the maximum weight for this box and theta for equilibrium. So we have two ropes. One of them ABC, another BD, and you see the shape. The theta here is unknown. The weight for this box is hanging here, it is unknown. But we know each rope can sustain to maximum load of 100 pounds. So, what is the maximum weight we can apply here? What is the maximum weight for the box we can hang here? And what is the theta for that? Okay, thank you so much for watching this lecture. See you next session. Bye.